not be real. So the computation is very expensive in federated learning if you use large neural networks. And the split learning, as explained, there is severe straggler problem in that. So the communication becomes expensive. So considering these two disadvantages, what the current paper does is it tries to take the advantages of these two methods and tries to build the FedGKT. On the overview, a very high level idea is you have several smaller networks, and we transfer knowledge from these to a larger one, which has a higher capability to obtain higher accuracy. Well, how exactly do we do it? I'll explain in the following slides. Again, I'll introduce another small preliminary, which may be important to know. It is about the knowledge distillation. So what is knowledge distillation? Like the name suggests, it's the process of transferring knowledge from a large model here, let's say it's called the teacher model, to a smaller model called the student model without losing any validity, without loss of accuracy. So how it exactly does is we have a data set on which the teacher is already trained. It is pre-trained network. And then we use the same data set later on to do the training of the student. So the student trains on this data and it produces the loss. And it looks at what was the teacher's loss that was produced. And there is a difference it computes using the cross entropy and the KL divergence. So it uses these two laws, let's call it distillation loss in combination. So the goal of the student network is to minimize the distillation loss by looking at what was the loss that the teacher produced. So it tries to imitate or mimic the way teacher had learned, and that is the way the student learns. So this way, the knowledge is distilled from the teacher to the student, and by this transfer of knowledge, the student is able to train better. Uh, the reason why do we need to do so much of training? Can't we just do the training like normal way? What is the reason behind why we need KD is the large models, very deep neural networks, usually have higher knowledge capacity than the small models. That is one reason. But unfortunately, it is computationally very expensive. Whereas the smaller models, though they do not learn so well like the teachers because they're smaller in size, they're computationally very less expensive. So the whole idea is you have a teacher and the student is trained from the teacher, and then the inference, we deploy the student so that the student has some very strong, robust classifier because it learned well from the teacher. And it is computationally less expensive, so it does two jobs at once. So this is what knowledge distillation on a high level is. Using these three concepts, the split learning, federated learning, and knowledge distillation, I will further introduce the current paper called the group knowledge transfer. What they do is they try to reformulate the federated learning problem in this way. Let's say on the server, you have a big network like ResNet 56 or ResNet 110, a full-fledged network. And on the student side, instead of using the proper split learning, we use a different way of doing it. On the student side, you have a very smaller network like ResNet 8, which in itself is self-sufficient. It has the convolutional layers, it has the bottleneck layers, it has the fully connected layers. So it has the feature extractor and classifier in itself, but it is way, way smaller compared to the teacher's network. So it is like a split learning plus KD over here. So these are the two CNN architectures they propose on the edge and on the server side. Going into more details, they do a alternating and periodical knowledge transfer. So this figure gives a overall architecture view of the FedGKT. So before I go to the steps, so on the left side, you have the edge, which means that you have the compact CNNs, several students or several edge devices. They all have a feature extractor in itself, and the small yellow block you see next to it contains the output of the feature extractor, which is nothing but the hidden vectors or the feature extraction vector. And after that is your classifier layer. And the output of the classifier is the output, it is the logits, and the pink is the predictions. So on the left, you have the edge devices, and on the right, you have the server. The server, again, has the logits, and it has its own predictions or the soft labels. So the method is for one global iteration, what happens is similar to federated learning. First, we have the local training where the client does the local steps of probably SGD or ADAM. It can use any such optimizers. And after all the local trainings, all the edge devices generate the hidden vectors from the feature extractor, and they send these as step 2 as a periodic transfer to the server or the teacher. And the larger server model is trained by taking these features using the knowledge distillation based loss function. What is the different thing here from other compared to other KDE papers is, while we saw that the student was learning from the teacher alone, in this paper, both are learning from each other. The student uploads his logits and the hidden vector to the server or the teacher. The teacher also trains right now because the server doesn't have any data access. Like in federated learning, we do not share any data. So the server doesn't have any data. This time it only looks at the logits and the hidden vectors sent from the students. It aggregates them and then does his own training and transfers back the logits. And the student, after receiving the logit from the teacher, it uses the KD-based loss function and it does the minimization of loss on his side. So we see a bidirectional mutual learning that happens simultaneously. The end result, once the training is completed, is you have an edge-sided model, which constitutes of a very robust feature extractor, which can be deployed at the inference stage confidently. This, along with the global shared model that the server trained. So you have a combination of the extractor and a global model. The other advantage of this method is the global model over here did not look at any data, but it was trained indirectly, taking the features of different types of devices over here. So this is also a kind of extension to personalized federated learning, a little bit of that, because each devices will have different data. So the data is non-IID. So this is how
One question.
Yes.
Sorry to interrupt. So for this case, both the server and the client, they will share a common data set, right?
No, they do not share the data.
So the server doesn't have any data at all.
No, the server doesn't have any data. However, it has the labels from the students. The edge devices, yeah, because if to do the cross entropy loss, you want to minimize the difference between the soft labels and the actual labels, the ground truth. So for that, the edge devices share only the labels with the server, not the data.
Okay, so how do we like calculate the loss value at the server?
Yeah, I can just show it in the next slides.
Okay.
Yeah, I'll come back to this question. I'll just put it on hold.
Okay.
Yeah. So just showing this same picture in a more mathematical way. You have all the students on your left. You have feature extractor. X is your input vectors. W is your extractor weights. H is your hidden vectors, and WC are your classifier weights. And the Y are the labels of each of the device. So we send Y, H, and the logics to the server for doing the classification. So the immediate benefit we see from this method is the communication bandwidth saving. Because if you want to transfer the gradients or the model updates or the weights, it is usually bigger in size. But the hidden vectors, on the other hand, is a little smaller in size. So the substantially uses lesser communication of all the compared to all the model parameters. And showing the same in a little bit of the algorithm, I'll just highlight a couple of important steps. The first step being the server broadcasts the logits to the client, and he also does his own training. And on the client side, the client obtains the logits sent by the server, and it uses that to compute the loss. I'll give you the loss formula in the next slide, so maybe it will be easier to follow it. And then it computes the hidden vector, the logits, and the labels, and sends it to the server. So the federated learning can be seen as a distributed optimization problem, and we know that the main global objective is to minimize the loss function of every local client over here, which is a weighted summation of the local updates, where n is the number of updates and a number of data points. So the Fed GKT reformulates this federated learning problem into two parts. Because we're using one on the server and one on the client side, we kind of split the FW into FS for the server and FC for the client. So the objective is to minimize the loss function LS of on the server side. And his constraint is the hidden vector from, coming in from the extractor. And for the client side, his objective is to minimize his own loss function LC which again is dependent on the HI. Here, as we can see, the inner optimization HI becomes very important because every client has to solve is expected to adequately solve this inner optimization very accurately, because the entire training is kind of dependent on H, because the server does not have your data or there's no other way to do the training. H becomes a very important parameter here. So the training has to be really adequate. And the other challenge that this method has is there's a correlation between the inner and the outer optimization. So for seeing this equation, the value of H, the quality of H is really important. It is dependent on that. But for H to be solved, the H is dependent on the LC, which again comes through the output of the server. So because of this mutual learning, there is kind of a correlation between the two. So to solve this was the main intention why they introduced the knowledge distillation part, where the easier way to solve that becomes by using the Kale divergence loss. So the Kale divergence loss attempts to bring the soft label as well as the ground truth, your Y, close to each other by absorbing the knowledge gained. So, I'm answering the question that was just asked over here. So the loss function on the server side is the cross entropy loss, which is nothing but the logarithmic difference between the ground truth and the soft labels. And the LK, the knowledge distillation loss is nothing but the KL divergence between the probabilistic prediction between the edge and the server models. So the PK and PS over here are the probabilistic predictions, and they are dependent on the logits that are generated from your fully connected layers. And T is a temperature hyperparameter, which is nothing but the softmax temperature, which determines how much soft your labels are, how soft your distribution is. So the intention is to try to minimize the distance between the two, and we use that as the KL divergence loss in combination with the normal cross entropy loss. This in combination becomes the loss value on the server side that he tries to minimize. And similarly, on the every client, on each of the client mobile device, we have the similar thing of trying to minimize the KL divergence between the PS and PK this time, because it is asymmetric. We see it PS and PK over here. That in combination with his own cross entropy loss will give us the loss value of the client. One advantage of computing the LCE over here is the client himself has both X and he has the X and Y, the data set as well as the labels. So it is easier to compute the cross entropy loss over here. But the challenge for the server is that the server does not have any data points or it doesn't have any labels. So it is difficult to compute the LCE. So for this reason, the edge models send the labels, send each of the edge device sends their own labels to the server. So the server is able to compute the LCE and he'll be able to compute the actual loss functions. Did I answer your question, Professor?
Yes, thank you.
Okay. So moving on, all the things that we just saw, just putting that in the, so from the previous slide, we saw how the problem was reformulated. Now, after introducing the knowledge distillation and the KL loss part, we try to substitute it back and we try to provide an improved version of the reformulated problem. So on the server side, we see that we substituted the part for the LKD. So the knowledge distillation loss has also got added to it. And our constraint not only has the hidden vector, we also try to write about the ZS. ZS is nothing but the logics. And on the client side also, we try to substitute it. And the constraint now also has the logics from the server and the logics from the client. Now, the reason why in knowledge distillation, we usually transmit the logics instead of sending the complete model or the W is instead of learning the predictions, learning how the prediction was made becomes really important for the student to learn from the teacher. So that is the reason we send the logics so that the entire vector can be seen at and we can see what was the wrong answer or what was the correct prediction. Or if there is a correct prediction, the student can kind of observe the graph and see what led the teacher to do a wrong prediction before. And he can look at the entire output, he can look at the entire logics vector and be able to make a decision. So this is how it will be able to learn more. So this paper tries to use the alternating minimization to solve this optimization problem. It first tries to fixes the weights on the server and then tries to optimize the weight on the client. And in the next iteration, it tries to fix the weight on the client and try to solve it on the server. So it uses this alternating minimization to solve this problem. Before I move on to the experiments, do you all have any questions so far? Okay, I will move on to the experiments part. So this paper uses their own framework called the FedML. It is an open source federated learning research library, which is open to all. They try to implement several kind of federated learning papers, from federated averaging to their own GKT and many FedProcs and many popular federated learning methods can be run using their framework. They have a server node with 4 NVIDIA RTX GPUs, and they have CPU-based nodes which act as clients for training smaller CNNs. They used Jetson TX2. They also use Raspberry Pi, and they have set up like that. And for the test, they use 3 data sets: the CFR10, CFR100, and CNIC 10. They use both IID as well as non-IID to show the improvement. And they use 16 edge clients in most of the experiments. And for the baseline comparisons, they use the vanilla federated averaging, the standard federated learning method. And the second baseline they use is the split learning based method, which we saw earlier in the preliminary. They use these two as the baseline. And the model architecture they use is they use the bigger ones like ResNet 56 or ResNet 110 on the server side. And on the edge side, they use a smaller neural network, which is the partitioned one on the clients like ResNet 8. ResNet 8 it has a 8 convolutional neural network, so it is a self-sufficient, contained smaller neural network in itself. So based on these experiments, they try to look at the test accuracy of both the models on the 3 data sets. On the server side, we see 2 of these rows talk about the server having ResNet 56 and ResNet 110. And in the methods, FedJKT is their own one, the one in bold. For the client, they're using ResNet 8. And for federated averaging, because they do not have this kind of a splitting method, the server and the client usually uses the same model. So on the client side, they have ResNet 56. And they also compare it with the centralized machine learning, which is not the federated learning, but the centralized machine learning models. They try to do the experiment on both the ResNet 56 as well as ResNet 8. And we see for all the 3 data sets, be it IID or non-IID, we see that the test accuracy, the performance is superior compared to the other methods, especially for non-IID. And for IID, it is kind of nearly very, very close to the federated average, like we see. And they show the tabular one in the more pictorial way. Here we see the test accuracy versus the number of communication rounds taken. We see that the Fed GKT takes much lesser communication rounds in comparison with the other methods. It is almost the same as the federated averaging, but it attains good accuracy compared to the federated averaging. And compared to the centralized methods, it is very more advantageous. It has better accuracy. And other than the accuracy evaluation, they try to look at how efficient the model is. First, they look at the computational efficiency on the edge side. So they use all the 3 models, ResNet 8, 56, and 110. The ResNet 8 being on the edge. And they try to measure the petaflops and the number of parameters and the CPU seconds it takes, the CPU running time for every mini batch in milliseconds. So as we can see that compared to the federated averaging baseline, the computational cost on the edge of the Fed GKT is 9 times lesser than that of ResNet 56 and more like 17 times less than that of ResNet 110. So we see that it is more computationally efficient compared to the other methods. And the second efficiency they check is how communication efficient this is. And for communication efficiency, they are mainly checking against the split learning, because split learning was the paper which had severe expensive communication. And for computation, we saw that federated learning was more computationally expensive. So this is why they compare with only split learning over here. And like we see on all the 3 data sets, FedGKT uses fewer feature map exchanges with the server compared to the split learning. And the other type of evaluations they do is by increasing the number of clients or the number of edge devices. They go from 18.8 to 128. They see that adding more edge devices does not really negatively affect the accuracy. The accuracy kind of almost remains the same, just goes a little bit of up and down, but not a lot of difference. And the other evaluation they do is to know how small we can go. We tried all this time with ResNet 8, but what if we try to use a much, much smaller model like ResNet 6 or ResNet 4? What happens then is they see that when the model size is reduced much, much further, it reduces the overall accuracy a little bit. So there is some trade-off that you can go to how small you can keep your edge device to. So this is one of the experiments. So these were all the evaluations. I next have the conclusion. So we saw that FedGKT is very memory and computational efficient compared to the split learning. It reduces the communication frequency by training in a local SGD manner, like the federated averaging. We saw that it reduces the communication bandwidth requirement by exchange of hidden features, as in the split learning, as opposed to exchanging the entire model or the model updates as in federated averaging. So we see that it naturally supports asynchronous training, which circumvents the severe synchronization issue in the split learning. I also have a small discussion pertaining to the methodology here. One is about the privacy and robustness. What the authors argue is that since the hidden map exchange happens instead of the gradient or the model update, and also because it happens at the training phase, the attacker's access is kind of limited to this evolving and untrained feature map. While that is a plus point, the minus point is that given that the model and gradient exchange may also leak privacy, any lack of analysis between these hidden map or the gradient is a limitation because that analysis is really not explored much. So you can still argue that there can be some leakage of information and some attack can take place. And the other is about the communication cost. So compared to the entire weight, model weight or gradients, hidden vector is definitely much smaller. But if you have a very, very large data set with several data points, then the image resolution is high. If the image resolution is also high, then of course it takes a little longer to finish the training. So the communication cost may increase a little bit. And the other problem is the label deficiency. So the FedGKT has one drawback. That is, it can only work on supervised learning. The reason being the cross entropy loss that we just saw earlier. The cross entropy loss needs the labels because it tries to minimize the difference between the ground truth and the soft labels. So without the labels, this cannot work. So that's why for now, this can only work for supervised learning settings. And the other discussion is about the model personalization. So we see that the final trained model is a combination of the global server model, which was trained using the hidden vectors of several clients, and also because of the client model. This helps the clients to learn more personalized ways. So for example, we can try to fine tune the client model for several more epochs and achieve some amount of personalization. So this is a discussion we had about this. That is all I had from my side. Thank you for listening. If you have any questions, please feel free to ask them.